of the global settings. And finally, we have the life cycle modeling part that you can, at the minimum, mention the entry point, but you can also specify a sequence of functions to be executed sequentially with some control flow constraints based on the return value. This is also to avoid some, very specific, again, test driver, especially it is a big challenge to link things with the system code. Okay, so I'm going to give you some ideas about the type of modeling available in prompt. First, for the functions, let's assume that we have function foo. Of course, it may have a return type, and it will have certain parameters in the body. So let's see what we can do. We may just decide to abstract the base foo, not execute it, and then we can say that, okay, we will be symbolizing the return value. Now, if this is a pointer, of course, through lazy initialization, you will get a valid object created as the pointer gets accessed, but you can also consider whether you want to also consider the null value as an option. Now, this really depends on your goal and what you think the role of foo is in your analysis in the system under analysis. Now, if foo is an entry point, for the arguments, you can, especially for the primitive ones, you can either initialize with a constant value or a symbolic value. And if it is a pointer type, since this could as well represent an array, right, you may want to think about the size of the array. Now, you can come up with a constant array size, or you can just write a relational constraint and saying that, the size of this array is maybe smaller than or equal to another argument in this function. And also, like, if this is a function for not necessarily an entry point and you're, again, modeling it, maybe it has some side effects, right? Then you may want to decide whether you want to havoc the pointer argument so that, we would see what would be the potential side effects, like over approximating. And in terms of the body, now it may have some inline assembly. You may want to say, okay, if it has inline assembly, I just want to get rid of the body, not execute it at all, or you may choose to execute it. But for the inline assembly, if it has a return value, just symbolize the return value. Now, memory allocation and deallocation of operations are obviously so important because we're targeting memory vulnerabilities at the end of the day. And some APIs actually have some weird signatures, right? Like some of them return the addresses, but some of them actually store it in one of the arguments. So prompt provides a variety of ways to specify those. You can also replace foo with another model function. Like if it ends with a pros suffix, it automatically does it. You don't even need to mention it. And also, you can specify sequence of functions to be executed with certain control flow constraints. Now, what type of options do we have for data types? Well, we can decide that a certain struct type is actually singleton. So if ever it gets created, there will only be one copy that will be used throughout the execution. If we have function pointer fields, we may want to just set them to null or a specific function. If we have primitive fields, again, we can constrain them with constants or in a relational way, referring to another field in the same struct type. Again, for the pointers, we need to decide the array size and so on. An interesting type of modeling we have for data types is the embedding relationship. So if we have a field that is another struct, by the way, this pointer is actually kind of a typo for this example. It shouldn't be a pointer. But if we have such embedding relationship, we can also specify those, and I'll explain why. Excuse me, it would be interesting and useful in the next slide. So in systems like the Linux kernel, this is pretty common. So what happens is that a generic data type gets embedded inside a custom data type. And so in certain contexts, we may have a pointer to the embedded object, and then pointer arithmetic is performed to drive a pointer to the outside object. But since we are performing component level analysis, we may not have the sufficient information at that level. And then the pointer we compute may be out of bound access, right? This is the curse of being so precise in symbolic execution. So what we need to do is we need to tell prompt that actually struct A embeds struct B, so that anytime that struct B would get created as part of lazy initialization, it would be placed inside struct A. And this way we would avoid this false positive memory out of bounds error and hopefully go and reach the deeper bugs that we are after. So this is just a simple example. And actually, if you look at the GitHub repo, we have a nice tutorial that we presented at SecDev 2020, and you will see examples like this. So if you want to understand more about semantics of prose, you will see examples like we have a prose API model here. It just says who is the entry point and type A, and that's type B. And as you see in this example, we have the simple struct A really embedding struct B. And then this is the container of macro kind of used in the Linux kernel for that pointer arithmetic that I just showed you. So let's say that if we analyze foo and we have a pointer to B, the embedded object, right? Because of our modeling, we can easily compute a pointer to the A object, the container object, and then you'll see that actually we will not get any memory errors at these lines. And you can actually, there's a virtual machine instance that you can also download, and if you follow these commands, you can reproduce those stuff. So one of the ways we evaluated prompt, we applied it to BlueZ, meaning that we wanted to reproduce some important vulnerabilities like remote code execution, and see what it takes to reproduce such vulnerabilities. This benchmark and the others are again available on the GitHub repo, and you can also reproduce it on the VM if you want to. Let's see. So what is happening here is that the error is in the parsing logic about the configuration options. So there is a local buffer of size 64, but since the size of the options is user controlled, it is possible that when this function gets called, the pointer may be advanced out of the array, and then we get a memory out of bounds write error. So because there is no actually check on the pointer whether it's going out of bounds. So of course, in the fix, they included the check. So what does the prose model look like? First of all, we have some global settings saying that if you ever, lazily initialize the pointer, make sure it is at least 128. Of course, this has some relation to the buffer we are targeting. And then we wanted to symbolize the return values of the inline assembly. We didn't want to get rid of the AS functions with assembly because there are a lot of functions in the Linux kernel with such instructions, and they are mostly inline, so it's not easy to deal with those. Of course, you can always compile and turn off inlining. And so we are saying that, for this L2 cap chain data structure, it embeds actually a generic linked list of the kernel. This is because we can actually pass through this line and get into the actual code location, right? We don't want to get this false positive here. And then we also initialize some of the callbacks, which get actually also abstracted away later. And then some of the functions that are not directly related to the bug that we're after, you just say return only modeling and so on. And we also, as you see, we also mentioned some deallocation and allocation functions with different syntax. Feel free to explore. And we also wrote a model function. As you see the prose suffix, it will be automatically replacing this original function because it had a switch statement that caused path explosion. We just needed a certain type of option in this particular case. And finally, on a nice machine, prompt can detect this in 5 minutes. Okay, and the artist researchers mentioned that it was really challenging to find this bug. So of course we had some clues and so on, but I think this is a testament to the power of prompt and API modeling in general. And the other type of evaluation we did, we analyzed device driver subsystems. We wanted to analyze the probe and disconnect entry points of these drivers. So these entry points call registration and deregistration API. So we came up with models for these 3 subsystems for 57 drivers. We wanted to see what we are achieving using API models. So we compared coverage and error rate when we don't have API models and just lazy initialization. So what did we really get or achieve? So we have 2 kind of modes of prompt. One is fully manual. You're responsible for the whole model. And the other one, blue one, is like reduced effort because you're doing some of the modeling through your global settings, much more automated. The red one is the lazy initialization only and no API modeling. As you see, both instruction and branch coverage is much greater. And in terms of the error rate, this is the percentage of the paths that ended up with some error. All right. So as you see, with lazy initialization, we have very high error rate compared to reduced and full versions of prompt. And of course, this is an indicator of false positives. So we detected 2 new bugs using prompt. One is a null pointer reference in a sound driver, and the other one is a double free in the network driver. So what is happening here is an API misuse, and they are trying to unregister a device that has not been actually registered yet. And these are the patches we provided. So we think that prompt is a useful tool to analyze system code. Of course, there's the manual effort that you need to go through, but hopefully you can invest in this type of effort and reuse. That's the nice thing. And we would definitely thank our sponsors. And for future work, what we're trying to do is automatically generate those API models. And thanks so much for your